right now, as you listen to this, the calcium in your bones, the iron in your blood, the oxygen filling your lungs. None of it was here when the universe began. 14 billion years ago, when the cosmos was newborn and still glowing with the heat of the Big Bang, only the simplest atoms existed: hydrogen, helium, and a trace of lithium. That was it. No carbon, no oxygen, no nitrogen, no iron. None of the elements that make up your body, your planet, or anything you have ever touched. Every single one of those heavier atoms was forged inside a star. Some were cooked slowly over billions of years in a stellar furnace not so different from our own sun. Others were born in a fraction of a second, in the violent death scream of a star 10 times heavier, blasted outward in an explosion so bright it briefly outshone an entire galaxy. The gold in a wedding ring, the silicon in a computer chip, the phosphorus in a strand of DNA. All of it was manufactured in the hearts of stars that lived and died long before our solar system existed. You are, quite literally, made of dead stars. And that is not poetry. That is chemistry. Think about that for a moment. The atoms in your left hand may have come from a different star than the atoms in your right. The carbon in your muscles was likely forged in a red giant star that swelled and pulsed somewhere in the Milky Way. Perhaps 6 or 7 billion years ago, the iron in your blood was almost certainly produced in the final second of a massive star's life, in the blinding fury of a supernova, and then scattered across light years of space before it was eventually swept up into the cloud that would collapse to form our sun and its family of planets. But how does a star go from nothing, from a wisp of cold gas drifting through the emptiness of space, to a roaring engine of nuclear fire, and then, eventually, to a quiet ember cooling in the dark for longer than the universe has existed? How does a formless haze of atoms become something so structured, so powerful, so self-sustaining that it can shine for billions of years? And what determines whether a star dies with a whisper or with a scream? That journey from dust to light to silence is one of the most extraordinary stories that nature has ever told. It is a story that plays out across timescales so vast they defy human comprehension. From the 100,000-year gestation of a protostar to the 10 trillion-year lifespan of the smallest red dwarf, it involves temperatures from 10 degrees above absolute zero to hundreds of billions of degrees. It involves objects smaller than a city and others larger than our entire solar system. And it involves physics that ranges from the quantum mechanical behavior of subatomic particles to the warping of spacetime itself. Tonight, we are going to tell that story. All of it, from beginning to end. So settle in, get comfortable, dim the lights if you like, because this is the life cycle of a star. To understand where stars come from, you first have to understand the space between them. And when most people imagine outer space, they picture a perfect vacuum, complete emptiness, blackness in every direction, punctuated only by distant points of light. But that picture is incomplete. The space between the stars is not truly empty. It is filled with something called the interstellar medium, a vast and diffuse sea of gas and dust that stretches across the entire galaxy, filling the gaps between stellar systems like an invisible ocean. Most of this material is extraordinarily thin. If you could scoop up a cubic centimeter of the interstellar medium you might find a single atom floating inside it. Compare that to the air you are breathing right now, which contains roughly 25 billion billions molecules in the same volume. The interstellar medium is, by any everyday standard, an almost perfect nothing. But almost is the key word, because scattered throughout this thin haze are denser pockets of gas and dust. Regions where the material has clumped together, drawn inward by its own faint gravity, or compressed by some passing disturbance. These are the molecular clouds, and they are among the most important structures in the entire universe. Molecular clouds are where stars are born. A molecular cloud is a vast region of space, sometimes stretching across dozens or even hundreds of light years, where the gas has become dense enough and cold enough to form molecules. The most common molecule in these clouds is molecular hydrogen. Two hydrogen atoms bonded together. But you will also find carbon monoxide, water, methanol, and even complex organic compounds, the early building blocks of the chemistry that will one day give rise to planets, and on at least one world that we know of, to life itself. These clouds are cold, staggeringly cold. Deep inside a molecular cloud, temperatures can plunge to just 10 degrees above absolute zero, which is negative 263 degrees Celsius. At those temperatures, the molecules move sluggishly, barely drifting through the dark. And the clouds are dark. They are so filled with microscopic grains of dust, particles of silicate, carbon, and ice, that they block the visible light from stars behind them. When astronomers look at a molecular cloud through an ordinary telescope, what they see is an absence, a dark patch against the glittering backdrop of the Milky Way, as if someone had taken an eraser to the sky. But when they switch to infrared or radio telescopes, the clouds come alive. Radio waves and infrared light can pass through the dust, revealing the structures hidden inside. And what they find is remarkable. These clouds are not smooth and uniform. They are turbulent, chaotic, shot through with filaments and knots and eddies. The gas swirls and churns, driven by magnetic fields, by the radiation of nearby stars, by the shockwaves of ancient explosions. It is a restless, dynamic environment, constantly shifting and reshaping itself. And somewhere inside that turbulence, in the densest knots where the gas has piled up beyond a certain critical threshold, gravity is about to win a very old fight. The composition of these clouds tells us something profound about the history of the universe. About 70% of the mass in a typical molecular cloud is hydrogen. About 28% is helium, and the remaining fraction, just 1 or 2%, is everything else. Carbon, oxygen, nitrogen, silicon, iron, all the heavier elements that were cooked up inside previous generations of stars and scattered into space when those stars died. Astronomers, in their peculiar shorthand, refer to all elements heavier than helium as metals, regardless of whether they are actually metallic in the chemical sense. In astronomy, oxygen is a metal. Carbon is a metal. Neon is a metal. The terminology can seem absurd, but it is useful. Everything that is not hydrogen or helium was forged inside a star. And so, the metal content of a molecular cloud is a direct measure of how much stellar processing has occurred in that part of the galaxy. Every molecular cloud carries within it the ashes of stars that came before. Every new star that forms is, In a sense, a phoenix rising from the remains of its ancestors. The most famous molecular cloud is probably the Orion Molecular Cloud Complex, which includes the visible Orion Nebula. That fuzzy patch of light you can spot with the naked eye in the sword of the constellation Orion. It lies roughly 1,300 light-years from Earth and contains enough material to make tens of thousands of stars. But there are molecular clouds scattered all across the galaxy. The Taurus Molecular Cloud, about 430 light-years away, is one of the closest star-forming regions to Earth and has been studied intensively. Within it, astronomers have found some of the youngest stars known, still wrapped in their cocoons of gas and dust, still in the process of being born. Giant molecular clouds can contain as much as 1,000,000 times the mass of the Sun. They can span over 100 light-years from end to end. And they are the starting point of everything that follows. Without these vast reservoirs of raw material, there would be no stars, no planets, no heavy elements, no life. The molecular cloud is the cradle of creation. It is worth pausing here to appreciate just how cold and how dark these places are. Imagine standing inside a molecular cloud. You would see nothing, absolutely nothing. The dust is so thick that starlight cannot penetrate. You would be surrounded by an inky blackness more complete than any night sky on Earth. The temperature would be just barely above the absolute minimum, so cold that most gases would freeze solid. And yet, paradoxically, these dark and freezing vaults are the most creative places in the galaxy. Everything that shines begins here, in the cold and the dark. The chemistry inside these clouds is surprisingly rich. Despite the frigid temperatures, chemical reactions do occur, driven by cosmic rays, ultraviolet radiation filtering in from the cloud's edges, and reactions on the surfaces of dust grains. Over 100 different molecular species have been identified in molecular clouds, from simple molecules like water and ammonia to complex organic compounds containing dozens of atoms. Recent research has shown that even at these early stages, the building blocks of the chemistry that will eventually give rise to planets and life are already being assembled. The molecular cloud is not just a reservoir of raw material. It is a chemical factory, quietly producing the ingredients for solar systems. The dust grains themselves are fascinating. They are typically just a fraction of a micrometer across, tiny specks of silicate, carbon, and ice. They form in the outer layers of dying stars and are blown into space by stellar winds and supernova explosions. Once in the interstellar medium, they serve as surfaces on which molecules can form, as shields that protect the interior of the cloud from destructive radiation, and eventually, as the seeds around which planets will grow. In a sense, the dust in a molecular cloud is already protoplanetary material, the earliest ancestor of the rocks and dirt beneath your feet. But a cradle needs a push. A molecular cloud can persist for millions of years, drifting through the galaxy in a state of uneasy equilibrium. The outward push of gas pressure and turbulence balances the inward pull of gravity, and the cloud hangs in suspension, cold and dark and quiet. Left entirely alone, it might never form a single star. But molecular clouds are not alone. They exist within a galaxy that is alive with activity, and sooner or later, something comes along to disturb the balance. The most dramatic trigger is a supernova. When a massive star at the end of its life explodes, it sends a shockwave racing outward through the interstellar medium at thousands of kilometers per second. When that shockwave slams into a nearby molecular cloud, it compresses the gas, squeezing the already dense regions into even denser knots. Suddenly, in those compressed pockets, gravity gains the upper hand. The gas begins to fall inward, and the process of star formation has begun. There is a beautiful symmetry in this. The death of one star triggers the birth of another. The universe recycles itself. But supernovae are not the only trigger. The spiral arms of our galaxy are themselves compression waves, density waves that rotate through the galactic disk, sweeping up gas and dust as they pass. When a molecular cloud enters a spiral arm, it gets squeezed, and star formation can be ignited on a grand scale. This is why spiral galaxies often have their brightest, youngest stars concentrated in their arms. Those arms are factories of stellar creation. Even the radiation and stellar winds from nearby massive stars can trigger collapse in a molecular cloud. The ultraviolet light from a hot young star can ionize the surface of a cloud, heating it and causing it to expand. But as the heated gas pushes outward, it compresses the cooler gas deeper inside, potentially triggering collapse there. Astronomers call this process radiative implosion, and it seems to be responsible for some of the most spectacular bursts of star formation in the galaxy. Whatever the trigger, the result is the same. Somewhere inside the cloud, a region of gas crosses a critical threshold. Its mass exceeds what physicists call the Jeans mass, named after the British physicist Sir James Jeans, who worked out the mathematics in the early 1900s. The Jeans mass is the minimum amount of material needed for gravity to overcome the outward pressure of the gas and begin pulling it inward. Once a pocket of gas exceeds this mass, collapse is inevitable, and so the cloud begins to fall in on itself, not all at once, but in fragments. As the cloud contracts, it breaks apart into smaller and smaller pieces, each one collapsing independently. This process is called fragmentation, and it explains why stars almost never form alone. They are born in batches, in clusters, sometimes in groups of just a handful, sometimes in swarms of thousands. The Orion Nebula, for instance, contains a dense young star cluster of several thousand infant stars, all born from the same parent cloud within the last few million years. Each of these collapsing fragments is destined to become a star, or at least to try. Some will not gather enough mass. They will collapse and heat up, but never quite reach the temperatures needed to ignite nuclear fusion in their cores. These failed stars are called brown dwarfs, and they occupy a strange twilight zone between the largest planets and the smallest true stars. Too massive to be a planet, too lightweight to be a star, they glow dimly for billions of years, slowly radiating away their heat of formation, and eventually fade into the dark. The boundary between a brown dwarf and a true star lies at roughly 8% of the Sun's mass, or about 80 times the mass of Jupiter. Below that threshold, the core of the collapsing object simply never gets hot enough, never crosses the roughly 10 million degree mark needed to sustain hydrogen fusion. The brown dwarf smolders, but never ignites. But for the fragments that do gather enough mass, the journey is just beginning. As the gas falls inward, it begins to rotate. This is a consequence of the conservation of angular momentum, a fundamental law of physics that says a spinning object spins faster as it contracts. Think of an ice skater pulling her arms in during a spin. The collapsing gas cloud had some slight rotation to begin with, inherited from the turbulent motions within the parent cloud. As the cloud contracts, that rotation speeds up, and the collapsing material flattens into a disk. At the center of that disk, where the material is densest and hottest, a protostar begins to form. The disk is important. It is not just a byproduct of the collapse. It is a key player in the drama. The disk acts as a conveyor belt, channeling material from the outer regions of the collapsing fragment down onto the protostar at the center. Without the disk, the angular momentum of the infalling gas would prevent it from reaching the center, and the protostar would be starved of material. The disk solves this problem by allowing angular momentum to be transported outward through turbulence and magnetic effects, while mass flows inward. It is also the structure from which planets will eventually form, making the protostellar disk the ancestor of every planetary system in the universe, including our own. A protostar is not yet a star. It does not shine by nuclear fusion. It glows because it is hot, and it is hot because it is being crushed. As material continues to rain down onto the protostar from the surrounding disk, the gravitational energy of the infalling gas is converted into heat. The temperature at the center of the protostar climbs steadily, from a few thousand degrees to tens of thousands, then hundreds of thousands. From the outside, you would not see much. The protostar is still buried deep inside its cocoon of gas and dust, invisible to optical telescopes. The dust absorbs the visible light and re-emits it at longer wavelengths in the infrared. This is why infrared telescopes, like the James Webb Space Telescope, are so important for studying star formation. They can peer through the dust and see the warm glow of protostars that would otherwise be completely hidden. The protostar is not a calm place. Material is crashing onto it from all directions, and the magnetic fields threaded through the collapsing gas are being twisted and amplified by the rotation of the disk. These magnetic fields channel some of the infalling material into powerful jets, narrow beams of hot gas that shoot outward from the protostar's poles at speeds of hundreds of kilometers per second. These jets can extend for light years, punching through the surrounding cloud and creating glowing shockwaves where they collide with the interstellar medium. Astronomers call these shockwaves Herbig-Haro objects, named after George Herbig and Guillermo Haro, who first identified them in the 1950s. They are among the most dramatic and beautiful features of star-forming regions. Bright knots and bow shocks of glowing gas that mark the violent birth of a new star. The protostellar phase is relatively brief by astronomical standards, lasting perhaps 100,000 years for a star like the Sun. During this time, the protostar is growing rapidly, pulling in material from the disk and building up its mass. The disk itself is also evolving. Small grains of dust within it are colliding and sticking together, growing into pebbles, then boulders, then larger bodies. This is the very first step in the formation of planets. Although that is a story for another time, the energy dynamics of a protostar are intense. The gravitational potential energy of the infalling material is converted into kinetic energy as it accelerates, and then into thermal energy when it crashes into the growing protostar. Half of this gravitational energy goes into heating the protostar, and the other half is radiated away. This is called the Helmholtz contraction, named after the 19th century physicist Hermann von Helmholtz, who was one of the first to consider gravity as an energy source for stars. Before the discovery of nuclear fusion, the Helmholtz contraction was the only known mechanism that could explain why the sun shines. Although it could only account for a few tens of millions of years of solar energy, far less than the billions of years that geologists were already insisting the Earth had existed. As the protostar grows, the temperature at its center climbs relentlessly. At first, the interior is entirely convective, with hot gas rising and cooler gas sinking in a churning, turbulent cycle. The protostar is essentially transparent to its own heat, and energy pours off into space at a prodigious rate. But as the density increases, the gas becomes opaque to radiation. Photons can no longer travel freely. Instead, they are absorbed and re-emitted countless times, slowly diffusing outward. This trapping of radiation causes the interior temperature to rise even faster. Some protostars are so deeply embedded in their parent clouds that they can only be detected as faint infrared or radio sources. Others, in slightly less dusty environments, can be seen as small dark silhouettes against brighter background nebulae. These dark, roundish blobs are called Bok globules, named after astronomer Bart Bok, who first suggested in the 1940s that they might be sites of star formation. Decades later, observations confirmed that he was right. Many Bok globules do indeed contain protostars in their cores, tiny points of warmth nestled inside cold cocoons of dust. A typical Bok globule is only a light year or so across and contains enough material to form a small handful of stars. As the protostar continues to contract and heat up, it eventually enters a new phase of its development. The surrounding envelope of gas and dust is gradually dispersed, blown away by the protostar's radiation and stellar winds. The protostar emerges from its cocoon, and for the first time, it becomes visible at optical wavelengths, but it is not yet a true star. It is something in between. It is a T-Tauri star. The T-Tauri phase is named after a particular young star, T-Tauri, which was first identified in the Taurus star-forming region back in 1852. It took almost another century before the astronomer Alfred Harrison Joy, working in 1945, recognized it as the prototype of an entire class of young, erratic, still-forming stars. Today, more than 500 T-Tauri stars have been cataloged, and they provide astronomers with an invaluable window into the early lives of stars like our Sun. A T-Tauri star is no longer hidden inside a thick envelope of dust. The powerful stellar winds and radiation of the young star have blown away much of the surrounding material, although a disk of gas and dust often remains, encircling the star like a flat ring. These are protoplanetary disks, and they are exactly what the name suggests: the raw material from which planets will eventually form. Roughly half of all T-Tauri stars younger than about 3 million years still possess these dusty disks by the time a T-Tauri star reaches 10 million years of age. Only about 1 in 10 still has a significant disk remaining. The material has either been swept up by the star, accreted onto growing planets, or blown away into space. T-Tauri stars are temperamental. They vary in brightness, sometimes dramatically, over timescales of days to weeks. Some of this variability comes from the disk, as clumps of material fall onto the star in bursts, releasing energy. Some of it comes from enormous star spots, cool patches on the star's surface caused by intense magnetic activity, similar to sunspots on our sun, but far larger and more dramatic. As much as 40% of a T-Tauri star's surface can be covered in star spots at any given time, causing significant fluctuations in its brightness as it rotates. And some of the variability is caused by the disk itself, as dense patches of dust pass in front of the star and temporarily block its light. The accretion process itself is remarkable to contemplate. Material does not simply fall straight down onto the T-Tauri star from the disk. The star's magnetic field, which is far stronger than the sun's, channels the infalling gas along magnetic field lines, funneling it down onto the star's surface near the magnetic poles. When this gas strikes the surface, it heats up to millions of degrees and emits ultraviolet and X-ray radiation. The result is that T-Tauri stars are surprisingly strong X-ray sources, much more so than older, more settled stars of similar mass. The X-ray emission is a telltale sign of their youth and their vigorous accretion activity. Another crucial aspect of the T-Tauri phase is the powerful bipolar outflows and jets that many of these stars produce. These jets, which can extend for light years in both directions, carry away excess angular momentum from the star disk system. Without this mechanism, the star would spin up so fast from accreting material that centrifugal force would prevent any further accretion, limiting the star's final mass to a small fraction of what it actually achieves. The jets essentially act as a brake, allowing the star to keep growing. Models suggest that without these jets, a star could not accrete more than about 5% of the sun's mass. The jets are not a side effect of star formation. They are an essential ingredient. Astronomers recognize two broad categories of T-Tauri stars. Classical T-Tauri stars still have extensive accretion disks, producing strong emission lines in their spectra as hot gas streams onto the stellar surface. Weak-lined T-Tauri stars, sometimes called naked T-Tauri stars, have either lost their disks or have disks so tenuous that they produce little observable accretion activity. The weak-lined T-Tauri stars are particularly interesting because they offer a relatively unobstructed view of the young star itself, free from the complications of disk emission. Our own sun is thought to have gone through a T-Tauri phase roughly 4.5 billion years ago, when it was still gathering the last of its mass from the solar nebula. During that time, the young sun would have been surrounded by the disk of gas and dust from which the planets were forming. The powerful solar wind of the young sun would have been much stronger than today's, and it would have played a role in clearing away the remaining gas in the inner solar system, leaving behind the rocky planets Mercury, Venus, Earth, and Mars. The energy of a T-Tauri star comes not from nuclear fusion, not yet, but from gravitational contraction. The star is still shrinking, still compressing, still converting gravitational potential energy into heat. A T Tauri star looks roughly like a main sequence star of similar mass in terms of surface temperature, but it is larger and therefore more luminous. It sits above the main sequence on the Hertzsprung-Russell diagram, slowly contracting and dimming as it approaches its final, stable configuration. This contraction phase is called the Hayashi track, after the Japanese astrophysicist Chashiro Hayashi, who worked out the theoretical details in the 1960s. Stars below about 3 solar masses follow this track, contracting more or less vertically downward on the Hertzsprung-Russell diagram, maintaining roughly the same surface temperature while their luminosity drops. Eventually, as the interior heats up sufficiently, a radiative zone develops in the core, and the star begins to move leftward on the diagram, growing hotter at its surface. How long this adolescent phase lasts depends entirely on mass. A very massive protostar, destined to become a hot blue giant of perhaps 17 solar masses, might race through this entire pre-main sequence phase in as little as 100,000 years. It barely spends any time as a visible T Tauri star before its core ignites, and it roars onto the main sequence. Our Sun, by contrast, took roughly 30 million years to complete its contraction, and the smallest stars, the red dwarfs with just a fraction of the Sun's mass, can take 500 million years or even longer to fully settle down. If a collapsing fragment does not accumulate enough mass, roughly 8% of the Sun's mass, its core will never reach the roughly 10 million degrees needed to sustain hydrogen fusion. The object will instead become a brown dwarf, a substellar body that glows faintly from residual heat, but never truly joins the ranks of the stars. Brown dwarfs are dim and hard to find, but they may be surprisingly common throughout the galaxy. They are the runts of stellar litters, born alongside true stars, but denied the mass they needed to shine. For those T Tauri stars that do make the cut, the moment of ignition arrives at last. Deep in the compressed core, the temperature crosses the threshold. Hydrogen nuclei, stripped of their electrons and moving at tremendous speeds, begin to collide and fuse. The star switches on, nuclear fusion begins, and the outpouring of energy stabilizes the star against further gravitational collapse. A delicate balance is established, the inward pull of gravity matched by the outward push of radiation pressure. The star achieves what physicists call hydrostatic equilibrium. My adolescence is over. The star has arrived on the main sequence, and this is where it will spend the vast majority of its life. The main sequence is not a place, it is a state of being. When astronomers plot stars on a graph with temperature on one axis and luminosity on the other, a pattern emerges. The vast majority of stars fall along a sweeping diagonal band running from the upper left, where the hottest and most luminous stars reside, down to the lower right, where the coolest and dimmest stars huddle. This band is the main sequence, and a star on it is doing one thing: fusing hydrogen into helium in its core. This graph is called the Hertzsprung-Russell diagram, named after the Danish astronomer Ejnar Hertzsprung and the American astronomer Henry Norris Russell, who independently developed it in the early 1910s. It remains one of the most powerful tools in all of stellar astronomy, a kind of family portrait of the stars that reveals their temperatures, luminosities, sizes, and even their ages and fates at a glance. Stars on the main sequence are also classified by their spectra, the patterns of light they emit. Astronomers use a system of spectral types designated by the letters O, B, A, F, G, K, and M, running from the hottest to the coolest. Generations of astronomy students have memorized this sequence with the mnemonic, "Oh, be a fine girl, kiss me," a phrase that dates back to the early 20th century when the classification scheme was being developed at Harvard College Observatory, largely through the pioneering work of women astronomers like Annie Jump Cannon and Cecilia Pangapishkin. Cannon, who classified the spectra of hundreds of thousands of stars by hand, was legendary for her speed and accuracy. She could examine and classify several hundred stellar spectra per hour, and her work formed the foundation of the Henry Draper Catalog, one of the most important astronomical databases ever compiled. It was Cecilia Pangapishkin, however, who made the truly revolutionary discovery. In her 1925 doctoral dissertation, widely considered one of the most brilliant theses in the history of astronomy, she demonstrated that the spectral sequence from O to M is fundamentally a sequence in temperature, and that stars are composed primarily of hydrogen and helium. This was a shocking conclusion at the time, because it overturned the prevailing assumption that stars had roughly the same composition as the Earth. Pangapishkin's work was initially dismissed, and she was even pressured to recant her conclusions about hydrogen abundance. But within a few years, the evidence became overwhelming and her findings were confirmed. Stars are hydrogen and helium machines, and their spectral classification tells us their temperature, which in turn tells us their mass, their luminosity, and their fate. Our Sun is a G-type star, sitting comfortably in the middle of the sequence with a surface temperature of about 5,800 degrees Celsius. More specifically, it is classified as a G to V star, where the 2 indicates a subtype within the G class, and the V indicates that it is a main sequence dwarf star. Each spectral class is subdivided into 10 numerical subtypes, from 0, hottest, to 9, coolest, giving astronomers a fairly precise temperature classification for any star. At the top of the main sequence sit the O-type stars. These are monsters. An O-type star can have a surface temperature exceeding 30,000 degrees and a luminosity more than 1,000,000 times that of the Sun. They are blue-white and blindingly bright, but they are also exceedingly rare. Their immense energy output means they burn through their hydrogen fuel at a staggering rate, and their main sequence lifetimes are measured in just a few million years. In cosmic terms, they barely flicker into existence before they die. Because they are so short-lived, O-type stars are always found near the regions where they were born, in or near molecular clouds and star-forming regions. They do not live long enough to wander far from their birthplace. At the bottom of the main sequence sit the M-type stars, the red dwarfs. These are the universe's slow burners. A typical red dwarf has a surface temperature of just 3,000 to 4,000 degrees and a luminosity that may be less than 1/10,000th of the Sun's. They are dim, cool, and incredibly long-lived, but we will return to them shortly because their story deserves special attention. Between these extremes lie the B-type blue-white stars, the type white stars like Sirius and Vega, the F-type yellow-white stars, the K-type orange stars like Arcturus, and all the subtle gradations in between. Each spectral type represents a different balance of mass, temperature, luminosity, and lifespan. The main sequence is not a line, but a continuum, a smooth gradient from the universe's brightest and most short-lived stars to its dimmest and most enduring. In the middle, stars like our Sun go about the business of fusing hydrogen into helium through a process called the proton-proton chain. This is a multi-step sequence of nuclear reactions in which 4 hydrogen nuclei, 4 protons, are ultimately combined to produce a single helium-4 nucleus, 2 positrons, 2 neutrinos, and a release of energy. The positrons immediately annihilate with electrons, producing gamma-ray photons, and the neutrinos stream outward, passing through the body of the star as if it were not there. In fact, the neutrinos produced in the Sun's core take only about 2 seconds to escape the star entirely, traveling at very nearly the speed of light. The photons, by contrast, have a much harder journey. They are absorbed and re-emitted countless times as they bounce through the dense plasma of the Sun's interior, taking a random, zigzagging path that can last for hundreds of thousands of years or more before they finally reach the surface and escape into space as visible light. Think about that. The sunlight warming your face right now was generated in the core of the Sun perhaps 100,000 years ago, during the last ice age, when woolly mammoths still roamed the Earth. It has spent all that time slowly working its way outward, photon by photon, through the dense interior, transformed from a gamma ray into the gentle visible light you see today. The Sun is not just a furnace. It is an incredibly dense, incredibly thick furnace, and the light takes an absurdly long time to find the exit. The rate of this process is astonishingly slow on a per-proton basis. Any individual proton in the core of the Sun will wait, on average, about 9 billion years before it successfully fuses with another proton. This is because the first step of the chain, the fusion of 2 protons to form deuterium, requires one of the protons to undergo a transformation into a neutron via the weak nuclear force, which is, as its name suggests, weak. The probability of this happening during any given collision is fantastically small. But there are so many protons in the Sun's core, roughly 10 to the 57th power, that even at this glacial per particle rate, the total energy output is enormous. The Sun converts roughly 600 million tons of hydrogen into helium every single second. And in the process, about 4 million tons of matter are converted into pure energy, according to Einstein's famous equation. 4 million tons of matter gone every second, transformed into the light and heat that sustain life on Earth. The Sun has been doing this for 4.5 billion years, and it has enough hydrogen left in its core to continue for another 5 billion. It is currently about 29% helium by mass in its core, with the remaining 70-odd% still hydrogen. But the composition is shifting year by year as helium accumulates and the star slowly, imperceptibly evolves. For stars significantly more massive than the Sun, roughly above 1 1/3 solar masses, the dominant fusion process shifts from the proton-proton chain to something called the carbon-nitrogen-oxygen cycle, or CNO cycle for short. This process uses atoms of carbon, nitrogen, and oxygen as catalysts. The carbon, nitrogen, and oxygen are not consumed. They participate in the reactions, get transformed from one isotope to another, and are eventually regenerated, while the net result is the same: 4 protons fused into one helium nucleus with a release of energy. The CNO cycle is enormously sensitive to temperature. Its reaction rate scales roughly as the 17th power of the core temperature, meaning that even a small increase in temperature produces a dramatic increase in energy output. A 10% rise in temperature can boost the CNO cycle's energy production by 350%. This is why massive stars, which have hotter cores, are so luminous. It also means that their energy generation is very tightly concentrated in the innermost part of the core, creating a steep temperature gradient that drives powerful convective motions, with hot plasma rising and cooler plasma sinking in a churning cycle. The German-American physicist Hans Bethe worked out the details of both the proton-proton chain and the CNO cycle in a landmark 1939 paper, work that would eventually earn him the Nobel Prize in Physics. Bethe showed that these two processes could account for the enormous energy output of stars, finally solving a puzzle that had baffled scientists for centuries. Before Bethe, no one truly understood why the sun shines. After Bethe, the answer was clear: nuclear fusion, the conversion of mass into energy deep inside the star. This fusion process, whether via the proton-proton chain or the CNO cycle, is what defines a main sequence star. As long as hydrogen fuel remains in the core, the star maintains its equilibrium. It is a self-regulating system, a kind of cosmic thermostat. If the fusion rate drops for some reason, the core contracts slightly under gravity, which raises the temperature and density, which increases the fusion rate, which pushes the core back out. If the fusion rate increases beyond the equilibrium point, the core expands, cools, and the rate drops back down. This negative feedback loop keeps the star remarkably stable over vast stretches of time. The star is a delicate balancing act between two forces. Gravity, pulling inward, is trying to crush the star into the smallest possible volume. And radiation pressure, pushing outward, is generated by the energy of nuclear fusion, trying to blow the star apart. As long as these two forces remain in balance, the star endures. The moment they fall out of balance, the star begins to change. And change, for a star, is the beginning of the end. For a star with the sun's mass, the main sequence lifetime is roughly 10 billion years. Our sun is currently about 4.5 billion years old, meaning it is roughly halfway through its hydrogen-burning phase. It has already consumed about half of the hydrogen originally present in its core, and it has another 5 billion years or so before the supply runs critically low. Stars more massive than the sun have shorter lifetimes because they burn their fuel so much faster. A star 10 times the sun's mass might spend only 20 million years on the main sequence. A star 50 times the sun's mass might last only a few million years, a blink of an eye in cosmic terms. Conversely, smaller stars live far longer. An M-type red dwarf with half the sun's mass could remain on the main sequence for 50 billion years or more, nearly 4 times the current age of the universe. And the very smallest red dwarfs can persist for timescales that make even the current age of the universe seem insignificant. Red dwarfs deserve their own chapter in this story because they are, in almost every meaningful way, the most important stars in the universe. They are the most common type of star by an overwhelming margin. Roughly 75% of all stars in the Milky Way are red dwarfs. 20 of the 30 nearest stars to our solar system are red dwarfs. The closest star to the Sun, Proxima Centauri, just over 4 light-years away in the constellation Centaurus, is a red dwarf. And yet, you cannot see a single one of them with the naked eye. They are simply too dim. A red dwarf has a mass between about 8% and 60% of the Sun's mass. Its surface temperature ranges from about 2,500 to 4,000 degrees Celsius, compared to the Sun's 5,800. Its luminosity can be as little as 1/10,000th of the Sun's. From any significant distance, a red dwarf is practically invisible. But what red dwarfs lack in brightness, they make up for in longevity. A red dwarf does not burn its hydrogen fuel the way the Sun does. In the Sun, only the hydrogen in the core is available for fusion. The core is surrounded by a radiative zone where energy is transported by photons bouncing around, and then a convective zone near the surface where hot gas rises and cooler gas sinks. But the hydrogen in the outer layers of the Sun never makes it down to the core. When the core's hydrogen is exhausted, it is gone, even though most of the star's total hydrogen supply remains untouched. Red dwarfs are different. Below about 35% of the Sun's mass, a red dwarf is fully convective. That means the entire star, from surface to center, is one giant churning convection cell. Hot gas rises from the core, carries its heat to the surface, cools, and sinks back down, bringing fresh hydrogen with it. This constant stirring means that a red dwarf has access to its entire hydrogen supply, not just the fraction in its core. It is the difference between burning the fuel only in the engine of a car versus being able to burn every drop of gasoline in the entire tank, seats, tires, and all. The result is an almost inconceivable lifespan. A red dwarf with about 10% of the Sun's mass could remain on the main sequence for roughly 10 trillion years. That is more than 700 times the current age of the universe. The universe is only 13.8 billion years old. Every red dwarf that has ever formed is still on the main sequence today. Not a single one has had time to evolve, to age, to die. They are all still in the prime of their stellar lives, slowly and patiently converting hydrogen into helium at a rate so modest that their fuel supply will last for eons upon eons. A red dwarf with about 16% of the Sun's mass, similar to the nearby Barnard star, could remain on the main sequence for roughly 2.5 trillion years, followed by another 5 billion years as a blue dwarf. The sheer abundance of red dwarfs is staggering. Astronomers estimate that the Milky Way contains somewhere around 200 billion stars, and at least 3/4 of those are red dwarfs. That means there are roughly 150 billion red dwarfs in our galaxy alone. And every single one of them will outlast every other type of star by an enormous margin. Despite their overwhelming numbers, red dwarfs are notoriously difficult to study. They are so faint that even the closest ones require a telescope to see. Proxima Centauri, the nearest star to the Sun at just 4.2 light-years, has an apparent magnitude of about 11, far too faint for the naked eye. The brightest red dwarf visible, without optical aid, may be Lacaille 8760, in the southern constellation Microscopium, which is barely visible under ideal conditions at magnitude 6.7. But in recent years, red dwarfs have become the focus of intense scientific interest, largely because of the discovery of exoplanets in their habitable zones. In 2017, astronomers announced the discovery of 7 Earth-sized planets orbiting the red dwarf TRAPPIST-1. About 40 light-years away, several of these planets lie within the star's habitable zone, the region where temperatures might allow liquid water to exist on a planet's surface. The discovery electrified the scientific community and the public alike. Could these tiny, dim, long-lived stars be the most promising places to search for life beyond Earth? The answer is complicated. Red dwarfs, especially young ones, are prone to violent flares, sudden outbursts of radiation that can bathe their close-in planets in ultraviolet and X-ray energy. A planet orbiting in the habitable zone of a red dwarf would be very close to the star, close enough to be tidally locked, with one face permanently turned toward the star and the other in eternal night. The combination of tidal locking, intense flare activity, and the potential for atmospheric stripping makes the habitability of red dwarf planets an open and actively debated question. But the mere possibility that life could develop around the most common type of star in the universe is tantalizing. When a red dwarf does eventually exhaust its hydrogen, it will not follow the same evolutionary path as a star like the Sun. It will not swell into a red giant. It lacks the mass to drive helium fusion. Instead, models suggest that as its hydrogen is consumed, a red dwarf will slowly grow hotter and more luminous, its surface transitioning from red to blue. It will become what astronomers call a blue dwarf, a theoretical stage that no star has yet reached because the universe has not existed long enough. After the blue dwarf phase, the star will contract into a white dwarf composed primarily of helium, and then begin the long, slow process of cooling toward oblivion. The red dwarfs will be the last stars shining in the universe. Long after every massive star has exploded, long after every sun-like star has puffed away its outer layers and faded to a cinder, the red dwarfs will still be there, glowing patiently in the gathering dark. They will be the final torchbearers of the age of starlight, carrying the flame for trillions of years to come. And when the last red dwarf finally sputters out, the era of stars will be over. But that is unimaginably far in the future. For now, let us return to a star more like our own Sun and follow its journey beyond the main sequence, into the strange and beautiful phases that come after the hydrogen runs out. For billions of years, a sun-like star sits contentedly on the main sequence, fusing hydrogen into helium in its core, maintaining a steady equilibrium between gravity and radiation pressure. But nothing lasts forever. Atom by atom, proton by proton, the hydrogen in the core is being consumed. Helium builds up in the center of the star like ash accumulating in a fireplace. And eventually, inevitably, the core runs low on fuel. When the hydrogen in the core is nearly gone, the fusion rate drops. The outward pressure decreases. Gravity, which has been patiently waiting all this time, begins to gain the upper hand. The core contracts. But here is the twist. The contraction heats the core, and that increased temperature ignites hydrogen fusion in a thin shell surrounding the now inert helium core. This shell burning produces more energy than the core ever did, because the shell has access to a larger volume of fresh hydrogen, and the higher temperatures drive faster fusion. The surge of energy from the shell pushes the outer layers of the star outward. The star begins to expand, slowly at first, then more dramatically. Its surface cools as it stretches, shifting in color from yellow to orange to red. The star is becoming a red giant. For a star with the sun's mass, the red giant phase is transformative. The star can swell to a diameter 100 times its original size or more when our sun eventually becomes a red giant. Roughly 5 billion years from now, its outer layers may extend past the orbit of Mercury, past Venus, and possibly to the orbit of Earth itself. The once familiar yellow dwarf will have become a monstrous, bloated, ruddy sphere, barely recognizable. Its surface gravity will be so weak because of the enormous increase in radius that the outer layers will begin to drift away into space, carried by a gentle but persistent stellar wind. The sun will gradually lose mass, shedding its outer layers grain by grain. The night sky from any surviving world in the solar system would be utterly transformed. Instead of a small, bright disk, the red giant sun would fill a significant portion of the sky. A vast glowing orb of deep orange red. The surface of the bloated star would be mottled and churning, with enormous convection cells, each one perhaps the size of the distance between the Earth and the sun, rising and falling in a slow boil. It would be a sight of terrible beauty, the death throes of the star that gave us life. Meanwhile, deep inside the star, the inert helium core continues to contract and heat up under the weight of the overlying layers. In stars between about half a solar mass and 2 solar masses, the core becomes so compressed that the helium enters a state called electron degeneracy. In this state, the electrons are packed so tightly together that they resist further compression, not because of thermal pressure, but because of a quantum mechanical principle called the Pauli exclusion principle. No 2 electrons can occupy the same quantum state. This degeneracy pressure supports the core against gravity, but it has a dangerous property. It does not respond to changes in temperature the way ordinary gas pressure does. In a normal gas, if the temperature rises, the gas expands and cools, which regulates the reaction rate. It is like a safety valve on a pressure cooker. When things get too hot, the valve opens, the pressure drops, and the system stays under control. But in degenerate matter, that safety valve does not work. Temperature can rise without causing expansion. The core is like a pressure cooker with the valve welded shut. So when the core temperature finally reaches about 100 million degrees Celsius, roughly 6 times the temperature at which hydrogen fusion occurs, something dramatic happens. Helium begins to fuse. The process is called the triple alpha process because physicists refer to helium-4 nuclei as alpha particles. 3 helium nuclei must come together almost simultaneously to form a single carbon-12 nucleus. this is an extraordinarily unlikely event. First, two helium nuclei collide to form berylliumate. But berylliumate is wildly unstable. It disintegrates back into two helium nuclei in less than 1/10 of a quadrillionth of a second. For the process to succeed, a third helium nucleus must collide with the fleeting berylliumate nucleus before it falls apart. The odds are vanishingly small on any given attempt, but at temperatures of 100 million degrees, the collisions are happening so frequently that a steady stream of carbon is produced. The existence of this process depends on a remarkable coincidence. The energy of the excited state of carbon-12, known as the Hoyle state, very nearly matches the combined energy of berylliumate and a helium-4 nucleus. This resonance greatly increases the probability of the reaction. The British astrophysicist Fred Hoyle predicted the existence of this energy level in 1953, before it had been experimentally confirmed, arguing that carbon is so abundant in the universe that there must be some mechanism to produce it efficiently. When nuclear physicist William Fowler confirmed the prediction in the laboratory, it was a stunning demonstration of the power of astrophysical reasoning. Hoyle had essentially deduced a property of the carbon nucleus from the observation that carbon exists in low-mass stars with degenerate cores. The onset of helium fusion is not gradual. It is explosive. When the core temperature reaches the ignition point, fusion begins throughout the entire degenerate core almost simultaneously, in an event called the helium flash. For a few minutes, the energy production in the core reaches a staggering rate, roughly comparable to the luminosity of an entire galaxy, some 100 billion times the sun's normal output. During the flash, the core burns through 60 to 80% of its helium in a matter of seconds. But this colossal burst of energy is entirely internal. None of it reaches the surface. Instead, the energy goes into lifting the core out of degeneracy, allowing it to expand and establish a new equilibrium. The star has survived its cardiac event. If you were standing on a planet orbiting such a star, you would notice nothing at all during the helium flash itself. The surface would remain calm and undisturbed, while a thermonuclear cataclysm raged in the core. Our sun is predicted to experience a helium flash roughly 1.2 billion years after it leaves the main sequence, which means it will happen in roughly 6 or 7 billion years from now. When it does, it will be one of the most extreme events in the sun's entire history. And yet, it will be invisible from the outside. After the helium flash, the star settles into a new phase of stability. Helium is now fusing into carbon in the core, while hydrogen continues to fuse in the surrounding shell. The star contracts somewhat, grows hotter, and becomes less luminous than it was at the tip of the red giant branch. On the Hertzsprung-Russell diagram, it moves leftward onto a region called the horizontal branch, where it will remain for roughly 100 million years, about 1/10 the duration of its main sequence lifetime. The triple alpha process is far less efficient at producing energy than hydrogen fusion, which is why the helium burning phase is so much shorter. During helium burning, some of the carbon nuclei fuse with additional helium nuclei to produce oxygen. The core gradually fills with carbon and oxygen, the two elements that will form the star's final legacy. The relative proportions of carbon and oxygen in the resulting white dwarf depend on the details of the stellar mass and the nuclear reaction rates. But typical white dwarfs are thought to be roughly half carbon and half oxygen by mass. These are the same elements that make up the core of our own planet and the backbone of every organic molecule. A reminder that the fate of dying stars and the existence of life are intimately connected, and when the helium in the core is exhausted, the star faces another crisis. Without core fusion, gravity once again squeezes the core. The carbon-oxygen core contracts, and helium fusion ignites in a shell around it, while hydrogen fusion continues in a larger shell farther out. The star expands again, even more dramatically than before, climbing the asymptotic giant branch. During this phase, the star becomes deeply unstable. The helium-burning shell is highly sensitive to temperature, and it undergoes periodic flashes called thermal pulses that cause the star to pulsate, swelling and shrinking rhythmically. With each pulse, the star sheds some of its outer layers, blowing material into space through powerful stellar winds. The mass loss accelerates. The star is disassembling itself, peeling away layer after layer. The material it ejects forms an expanding shell of gas around the star, enriched with carbon and other elements that were dredged up from the interior by the deep convective motions of the asymptotic giant branch phase. This process, known as the third dredge-up, can bring enough carbon to the surface that the star's atmosphere becomes carbon-rich rather than oxygen-rich, transforming it into a carbon star. Carbon stars have a distinctive deep red color and spectra dominated by molecular bands of carbon compounds. They are among the most efficient factories of interstellar dust, as the carbon in their atmospheres condenses into tiny grains of soot that are blown into space by the stellar wind. This is one of the primary ways that stars return processed material to the interstellar medium, seeding future generations of molecular clouds with the heavy elements needed to form rocky planets and living organisms. During the asymptotic giant branch phase, the mass loss rate can reach 1/1,000,000th of a solar mass per year, or even more in the most extreme cases. Compare this to the Sun's current mass loss rate from its solar wind, which is only about 100 trillionth of a solar mass per year. The dying star is losing mass 100 million times faster than the Sun. Over the course of a few 100,000 years, it can shed most of its remaining envelope, stripping itself down to its hot, compact core. The transition from an asymptotic giant branch star to a planetary nebula happens relatively quickly. In the final stages, the mass loss rate spikes dramatically in what is sometimes called a superwind, ejecting the last of the envelope in perhaps 10 to 20,000 years. This superwind can reach velocities of 15 to 25 kilometers per second, and the ejected material forms a dense shell around the star. As the envelope thins, the hot core of the star is gradually uncovered. Its surface temperature rises steeply, from a few thousand degrees to tens of thousands, and then to over 100,000 degrees in just a few thousand years. The searing ultraviolet radiation from the newly exposed core begins to ionize the surrounding shell of gas. The atoms absorb the energetic photons and re-emit the energy at specific wavelengths, creating the characteristic glow of a planetary nebula. Hydrogen glows red, doubly ionized oxygen produces a distinctive green light, and nitrogen contributes shades of blue and violet. The result is a cosmic light show of extraordinary beauty. And then, after a cosmically brief period of furious mass loss, the outer layers are gone. What remains is the exposed core of the star, now a small, intensely hot object about the size of the Earth, glowing with a surface temperature that can exceed 100,000 degrees. The expelled gas, illuminated by the scorching ultraviolet radiation of this exposed core, begins to fluoresce. It glows in the colors of ionized hydrogen, oxygen, nitrogen, and helium, creating one of the most visually stunning phenomena in all of astronomy, a planetary nebula. The name planetary nebula is a historical accident, a relic of early telescopic observations. When the astronomer William Herschel first observed these objects in the late 1700s, their round, greenish disks reminded him of the planet Uranus, which he had recently discovered. The name stuck, even though planetary nebulae have absolutely nothing to do with planets. They are, instead, the glowing shrouds of dying stars. A planetary nebula is ephemeral. The expanding gas moves outward at speeds of 20 to 30 kilometers per second. And within 50,000 years or so, it has dispersed into the interstellar medium, becoming too thin and too faint to be visible. In cosmic terms, a planetary nebula is a blink, a brief flash of beauty before the lights go out. But what beauty! Planetary nebulae are among the most exquisite objects in the sky. The Ring Nebula in the constellation Lyra, the Helix Nebula in Aquarius, the Cat's Eye Nebula in Draco. Each one is unique, shaped by the complex interplay of stellar winds, magnetic fields, and the surrounding environment. Some are nearly spherical. Others are elongated, bipolar, or fantastically irregular. Many have concentric shells, evidence of multiple episodes of mass ejection. The Hubble Space Telescope has captured images of these objects in breathtaking detail, revealing intricate structures that speak to the turbulent final moments of the star's life. One popular model for explaining the shapes of planetary nebulae is sometimes called the colliding wind model. The idea is that the fast stellar wind from the exposed hot core slams into the slower, denser material that was ejected earlier during the asymptotic giant branch phase. The collision creates a hot, compressed shell that emits light. The shape of the nebula depends on the geometry of the earlier mass loss. If the mass loss were spherical, the planetary nebula would be roughly round. But if the earlier mass loss was concentrated in a disk or along the equator of the star, perhaps due to rotation or the presence of a companion star, the fast wind will break through more easily at the poles, creating a bipolar or hourglass-shaped nebula. The planetary nebula phase is a crucial moment in the cosmic recycling process. The gas expelled by the dying star is enriched with carbon, nitrogen, oxygen, and other elements that were dredged up from the star's interior. This material mixes into the interstellar medium, enriching the pool of raw material from which future generations of stars and planets will form. In a very real sense, the death of each sun-like star makes the birth of the next generation of stars and planets possible. The cosmos is a closed-loop system, endlessly recycling its own materials. At the heart of every planetary nebula sits the remnant core of the star, now fully exposed and fiercely hot. This object is a white dwarf, and it is the final form that most stars in the universe will eventually take. In fact, about 97% of all stars in the Milky Way will end their lives as white dwarfs. They are the default endpoint of stellar evolution for all but the most massive stars. A white dwarf is extraordinary. It contains roughly the mass of the Sun compressed into a volume about the size of the Earth. Its density is staggering, something in the range of 1 million grams per cubic centimeter. A teaspoon of white dwarf material would weigh about 5.5 tons on Earth. To put that another way, if you could somehow transport a sugar cube-sized piece of white dwarf material to your kitchen table, it would weigh about as much as a small car. The atoms inside a white dwarf are packed so tightly that the electrons have been squeezed out of their usual orbits and exist in a shared, degenerate state, forming a kind of electron sea that pervades the entire star. The nuclei of carbon and oxygen sit in this sea like tiny islands in an ocean of electrons. It is this electron degeneracy pressure that supports the white dwarf against gravitational collapse. Unlike a normal star, a white dwarf has no internal energy source. No fusion is occurring. It is simply a hot ball of carbon and oxygen, slowly radiating its residual heat into space. In a very real sense, a white dwarf is not a star at all. It is a stellar corpse, a remnant, an ember. It shines not because it produces new energy, but because it is still hot from its previous life. And that word, slowly, does not do justice to the timescale involved. A newly formed white dwarf can have a surface temperature exceeding 100,000 degrees. It is an intensely hot object, blazing with ultraviolet radiation. But with no energy source to replenish the heat it radiates away, it gradually cools. The cooling process is governed by the opacity of the thin, non-degenerate atmosphere that sits on top of the degenerate core, like a blanket insulating the interior from space. This blanket is incredibly effective. For roughly the first 20 million years of a white dwarf's existence, the dominant cooling mechanism is actually neutrino emission from the hot interior, not photon radiation from the surface. Neutrinos, those ghostly particles that barely interact with matter, can escape directly from the core, draining energy from the inside. But after those initial millions of years, neutrino cooling becomes less important, and the white dwarf settles into a long, slow decline governed by photon radiation from its surface. After 1 billion years, its surface temperature might drop to about 20,000 degrees. After 2 billion years, it cools to around 8,000 degrees, and the core has begun to crystallize. After 5 billion years, the surface is still a few thousand degrees, warm enough to glow with a white or yellowish light, dim but steady. After about 15 billion years, a time slightly longer than the current age of the universe, the oldest white dwarfs have cooled to about 3,000 or 4,000 degrees, barely visible, fading toward the threshold of detectability. The coolest white dwarfs known today have surface temperatures of about 3,000 degrees, making them some of the oldest objects in the Milky Way. Relics of stars that formed when the galaxy was young. The Indian-American physicist Subramanian Chandrasekhar showed in the 1930s that there is a maximum mass a white dwarf can have about 1.4 times the mass of the Sun. Beyond this limit, now called the Chandrasekhar limit, electron degeneracy pressure is insufficient to resist gravity, and the star must collapse further. Chandrasekhar made this calculation as a young man of only 19, working out mathematics during a sea voyage from India to England to begin his graduate studies at Cambridge. The result was elegant, profound, and initially controversial. The great astrophysicist Arthur Eddington famously dismissed it, unable or unwilling to accept that a star could collapse beyond the white dwarf stage. But Chandrasekhar was right, and history has vindicated him. He won the Nobel Prize in Physics in 1983 for his work on the structure and evolution of stars. Deep inside the oldest white dwarfs, something remarkable has happened. As the temperature drops, the carbon and oxygen nuclei, which were initially in a liquid-like state, begin to arrange themselves into a crystalline lattice. The white dwarf is literally crystallizing from the inside out. It is becoming, in a sense, a cosmic diamond, a planet-sized crystal of carbon and oxygen drifting through space. In 2019, astronomers using data from the European Space Agency's Gaia spacecraft confirmed that white dwarf crystallization is widespread, finding evidence of it in hundreds of nearby white dwarfs. The crystallization process actually releases latent heat, much like water releasing heat when it freezes into ice, which temporarily slows the cooling rate of the white dwarf. This means that some white dwarfs may appear younger than they actually are, their cooling delayed by the slow release of energy as their interiors solidify. White dwarfs have another peculiarity. Because of the nature of degenerate matter, the more massive a white dwarf is, the smaller it is. This is counterintuitive. You might expect a more massive object to be bigger, but in a degenerate gas, adding mass increases the gravitational compression so much that the electrons are squeezed into even higher energy states, allowing the star to be packed into a smaller volume. A white dwarf at the Chandrasekhar limit is actually smaller than one with half the Sun's mass. Push the mass just slightly above the limit, and the star cannot exist at all as a white dwarf. It must collapse to something denser. Some white dwarfs exist in binary star systems, orbiting close to a companion star. In these systems, the white dwarf can gradually pull material from its partner, accreting a layer of hydrogen or helium on its surface. When this accreted layer reaches a critical mass, it can ignite in a thermonuclear explosion, producing a brief but brilliant nova, a flash of light that can make the white dwarf temporarily visible to the naked eye. If the accretion continues, and the white dwarf approaches the Chandrasekhar limit, or if two white dwarfs in a close binary spiral together and merge, the result can be a type Ia supernova, a completely different kind of stellar explosion from the core collapse supernovae of massive stars. Type Ia supernovae are extraordinarily consistent in their peak brightness, which has made them invaluable to astronomers as standard candles for measuring cosmic distances. It was through observations of type Ia supernovae that astronomers discovered in 1998 that the expansion of the universe is accelerating, a finding that led to the concept of dark energy, the theoretical endpoint of the cooling process for an isolated white dwarf is a black dwarf. A black dwarf is a white dwarf that has cooled so completely that it no longer emits any significant heat or light. It would be a dark, cold, invisible lump of crystallized carbon and oxygen, detectable only by its gravitational influence on nearby objects. But here is the thing: no black dwarfs exist. The universe is not old enough. The cooling process takes so long, perhaps a quadrillion years or more, that even the very first white dwarfs ever formed from the earliest generations of stars are still glowing today. They are fading, certainly, dimming, but they have not yet gone dark. The universe would need to be at least 100 times its current age before the first black dwarfs would appear. And so, the final fate of a sun-like star is a quiet one, not a bang, but a slow, patient fade. An ember cooling in the darkness, surrounded by the dispersing wisps of what was once a glowing planetary nebula, surrounded in turn by the enriched gas that will someday be gathered up by gravity into a new molecular cloud, where the cycle can begin again. But not all stars die quietly. For the massive stars, the ones that blaze at the top of the main sequence, the end is anything but gentle. A star needs to be roughly 8 to 10 times the mass of the sun or more to meet this violent fate. These are the supergiants, the bright blue and red behemoths that dominate the upper reaches of the Hertzsprung-Russell diagram. They live fast, burn hot, and die young. A massive star goes through the same initial stages as a smaller star. It forms from a molecular cloud, collapses through the protostellar phase, arrives on the main sequence, and begins fusing hydrogen into helium. But because of its greater mass, everything happens faster and at higher temperatures. The core is hotter, the fusion is more furious, and the hydrogen is consumed in just a few million years instead of billions. When the hydrogen in the core runs out, the star begins to fuse helium into carbon, just as a sun-like star does. But a massive star does not stop there. Its core is heavy enough, its gravity strong enough, to compress the carbon to the temperatures needed for the next stage of fusion. Carbon begins to fuse into neon and magnesium at temperatures of about 600 million degrees. When the carbon is used up, neon fuses into oxygen and magnesium. Then, oxygen fuses into silicon and sulfur. And finally, silicon fuses into iron. Each successive stage of burning is shorter and less efficient than the last. Hydrogen burning lasted millions of years. Helium burning lasts a few 100,000 years. Carbon burning might last a few 100 years. Neon burning lasts about a year. Oxygen burning lasts a few months. Silicon burning lasts a single day. The star is racing through its fuel reserves at an ever-increasing pace, desperately trying to stave off gravitational collapse. It is like a person burning through their savings, spending faster and faster, knowing the money will run out soon, but unable to stop. The star at this stage is in a state of extreme crisis. Its core is a raging inferno of competing nuclear reactions, each one producing less energy than the last, each one buying less time. The outer layers of the star may appear calm from the outside, still glowing as a red or blue supergiant, but the interior is a roiling disaster, a frantic sequence of nuclear transformations that is about to reach its inevitable conclusion. If you could peer inside a massive star at this late stage of its life, you would see a structure resembling an onion. with concentric shells of progressively heavier elements layered around the core. An outermost shell of hydrogen surrounds a shell of helium, which surrounds a shell of carbon, then neon, then oxygen, then silicon. And at the very center, a ball of iron and nickel about the size of the Earth. Each shell is fusing its particular element, adding mass to the next shell inward. It is a magnificent and doomed architecture, a star built in layers like a geological formation, each layer recording a chapter of its nuclear history, and then everything stops. Iron is the end of the line. Every fusion reaction before iron releases energy. That is what has been keeping the star alive. But iron has the most tightly bound nucleus of any element. Fusing iron into heavier elements does not release energy. It absorbs it. Iron is an energy sink, not an energy source. It is the dead end of stellar nucleosynthesis, the element beyond which fusion offers no salvation. When the core becomes predominantly iron, there is nothing left to burn. No more energy can be extracted. The furnace has gone out. The star, which has been fighting gravity for millions of years through a succession of increasingly desperate nuclear reactions, has played its last card. For a brief moment, the iron core is supported by electron degeneracy pressure, the same force that holds up a white dwarf. But the core is growing rapidly as the silicon shell continues to deposit iron onto it. Within hours or days, the core exceeds the Chandrasekhar limit of about 1.4 solar masses. The electrons are being squeezed into the nuclei, combining with protons to form neutrons in a process called electron capture. Each electron capture produces a neutrino, which escapes, carrying away energy and further weakening the core's ability to resist gravity. And then, in less than a second, the core collapses. The speed of the collapse is breathtaking. The iron core, which moments before was the size of the Earth, about 12,000 kilometers across, is crushed to a sphere roughly 20 kilometers across in a fraction of a second. The outer layers of the core plunge inward at speeds reaching up to 23% of the speed of light, nearly 70,000 kilometers per second. Temperatures soar past 100 billion degrees, hotter than the core of any star, hotter even than the conditions in the first seconds after the Big Bang. The iron nuclei are smashed apart into individual protons and neutrons by high-energy gamma rays, a process called photodisintegration. This is deeply ironic. In the star's final moments, the very elements it spent millions of years building are torn apart in an instant, undoing hundreds of thousands of years of nuclear fusion in a heartbeat. Protons are squeezed together with electrons to form neutrons, releasing an enormous flood of neutrinos. In roughly 10 seconds, the collapsing core produces about 10 to the 58th neutrinos, a number so large it is essentially meaningless to the human mind. If you could line up all the neutrinos from a single supernova side by side, they would stretch. Well, the comparison breaks down because neutrinos are point particles, but their number is almost unfathomable. The neutrinos carry away the vast majority of the energy released in the collapse, roughly 99% of it. In those few seconds, the collapsing core produces more neutrinos than the sun will emit over its entire 10 billion year lifetime. These ghostly particles, which normally pass through matter without a trace, are produced in such prodigious quantities that they actually deposit a significant amount of energy in the layers of the star just outside the core. Only about 1% of the neutrino energy is absorbed. But that 1% is more than enough to blow the star apart. The inner core, now composed almost entirely of neutrons, reaches nuclear density and stiffens. The infalling material from the outer core slams into this suddenly rigid surface and rebounds, generating a powerful shockwave that races outward through the star. For a moment, it stalls, losing energy as it plows through the dense, infalling material. But the flood of neutrinos from the newly formed neutron star at the center reinvigorates the shock, pumping energy into it from below. The shock breaks through. The star explodes. This is a core collapse supernova, one of the most energetic events in the known universe. The explosion can outshine an entire galaxy of 100 billion stars, pumping out more energy in a few weeks than the sun will produce in its entire existence. The material is blasted outward at speeds of up to tens of thousands of kilometers per second, carrying with it all the elements the star produced during its life: hydrogen, helium, carbon, oxygen, silicon, and more. The supernova remnant, the expanding cloud of debris, will glow for thousands of years as it plows through the surrounding interstellar medium, heating the gas and creating intricate structures of shock-heated filaments. The Crab Nebula, visible in the constellation Taurus, is one of the most famous supernova remnants. It is the expanding debris field of a star that was observed to explode in 1054 by Chinese and Japanese astronomers, who recorded a guest star that was bright enough to be visible in daylight for several weeks. At the heart of the Crab Nebula sits a pulsar, a rapidly spinning neutron star that rotates about 30 times per second, emitting beams of radiation that sweep across space like a cosmic lighthouse. But the supernova does something else as well. In the extreme conditions of the explosion, a torrent of free neutrons is released. These neutrons are captured by the nuclei in the expanding debris, building up heavier and heavier elements through a process called the R process, or rapid neutron capture process. Gold, platinum, uranium, and dozens of other heavy elements are forged in those few seconds of chaos. Everything heavier than iron that exists in the universe was created either in the crucible of a supernova or in the collision of neutron stars. Another spectacularly violent event: the gold in every ring, the uranium in every reactor, the iodine in your thyroid gland. All of it was born in moments of extreme cosmic violence. There is a certain star in the winter sky that has captured the public imagination as a potential future supernova: Betelgeuse, the bright red supergiant that marks the shoulder of the constellation Orion. Betelgeuse is roughly 700 light-years from Earth and has a mass estimated at around 15 to 20 times that of the Sun. It has already left the main sequence, exhausted its hydrogen fuel, and swelled to a monstrous size. If Betelgeuse were placed at the center of our solar system, its surface would extend past the orbit of Mars, perhaps even to the orbit of Jupiter. It is an aging giant, deep into the twilight of its stellar life, and it will almost certainly end in a core collapse supernova. When it does, it will be a spectacular sight from Earth, easily visible in daylight, possibly as bright as the full moon. but there is no need to worry about the explosion being dangerous. At 700 light-years, Betelgeuse is far too distant to pose any threat to Earth. The most famous nearby supernova in modern times is supernova 1987A, which occurred in the Large Magellanic Cloud, a satellite galaxy of the Milky Way about 168,000 light-years from Earth. Its light reached us on February 23, 1987, making it the closest supernova observed since Kepler's supernova in 1604. Remarkably, a few hours before the visible light arrived, underground neutrino detectors in Japan and the United States registered a brief pulse of neutrinos from the explosion. Just 25 particles in all. But it was enough to confirm the theory that core collapse supernovae are powered by the release of gravitational energy in the form of neutrinos. It was the first time neutrinos from beyond our solar system had ever been detected, and it marked the beginning of neutrino astronomy. The supernova's progenitor star turned out to be a surprise. Astronomers had expected only red supergiants to explode as core collapse supernovae. But Sanjalik negative 69202 was a blue supergiant. This forced a revision of models and a deeper understanding of the complex final stages of massive star evolution. The discovery demonstrated that nature is always more complicated than our theories predict, and that each new observation can overturn long-held assumptions. In 2024, the James Webb Space Telescope found the best evidence yet for a neutron star at the heart of the remnant of supernova 1987A, finally confirming what astronomers had suspected for decades. The collapsed core survived as a neutron star rather than collapsing further into a black hole. A neutron star is one of the two possible remnants of a core collapse supernova. If the remnant core has a mass between roughly 1.5 and about 3 solar masses, the collapse is halted by neutron degeneracy pressure. The resistance of neutrons, packed shoulder to shoulder, to be squeezed any further. The result is an object of almost incomprehensible density. A neutron star packs more mass than the Sun into a sphere about 20 kilometers across, roughly the size of a large city. A teaspoon of neutron star material would weigh about 6 billion tons. Neutron stars rotate rapidly, a consequence of the conservation of angular momentum during the collapse. A star that was rotating once every few weeks can, after its core collapses to a fraction of a percent of its original size, spin hundreds of times per second. It is the same physics as the ice skater pulling in her arms, but taken to an extreme that defies everyday intuition. The surface of a rapidly spinning neutron star can be moving at a significant fraction of the speed of light. Many neutron stars emit beams of radiation from their magnetic poles, and as they spin, these beams sweep across space like the beam of a lighthouse. If one of those beams happens to point toward Earth, we see it as a regular pulse of radio waves, X-rays, or gamma rays. These objects are called pulsars, and the discovery of the first pulsar in 1967 by Jocelyn Bell Burnell and Anthony Hewish was one of the landmark achievements of 20th century astronomy. Bell Burnell was a graduate student at the time, and she initially noticed a regular, repeating signal in the data from a radio telescope at Cambridge. The signal was so precise so regular that the team briefly considered the possibility that it might be an artificial signal from an extraterrestrial civilization. They gave it the half-joking designation LGM-1 for Little Green Men 1. Of course, the true explanation turned out to be even more extraordinary. A spinning neutron star, the collapsed remnant of a dead giant, broadcasting its rotation into the cosmos like a celestial metronome. Some neutron stars have extraordinarily powerful magnetic fields, trillions of times stronger than Earth's. These extreme objects are called magnetars, and they can release enormous bursts of energy when their magnetic fields rearrange. A single magnetar flare can release more energy in a fraction of a second than the sun produces in 100,000 years. On December 27, 2004, a magnetar called SGR 1806-20 sent a burst of radiation so intense that it measurably affected Earth's upper atmosphere from 50,000 light-years away. Had it been just 10 light-years distant, it could have posed a serious threat to life on Earth. Neutron stars also participate in one of the most dramatic events discovered in recent years: neutron star mergers, when two neutron stars in a close binary system gradually spiral inward due to the emission of gravitational waves. They eventually collide and merge in a cataclysmic event that produces both gravitational waves and a burst of electromagnetic radiation across the entire spectrum. The first direct detection of gravitational waves from such a merger came in 2017, when the LIGO and Virgo observatories detected the event known as GW 170817. Telescopes around the world observed the accompanying electromagnetic flash, called a kilonova, and confirmed that these mergers are a major source of heavy elements, perhaps producing even more gold, platinum, and uranium than supernovae do. But if the remnant core is too massive, even neutron degeneracy pressure is not enough to resist gravity. Above approximately 3 solar masses, though the precise limit remains uncertain and is a topic of active research, the core cannot stabilize. There is no known force in physics that can halt the collapse. The matter compresses past the density of a neutron star, past the point where our current understanding of physics breaks down and a black hole forms. A black hole is a region of space-time where gravity is so extreme that nothing, not even light, can escape. At the center lies a singularity, a point of theoretically infinite density where the laws of physics, as we know them, cease to apply. Surrounding the singularity is the event horizon, a boundary beyond which there is no return. Anything that crosses the event horizon, matter, light, or information, is lost to the outside universe forever. The event horizon is not a physical surface. You would not feel it as you passed through. It is simply the point beyond which the escape velocity exceeds the speed of light. Once you cross it, your future, all possible futures, lead inward toward the singularity. There is no outward direction anymore. It is as if the center of the black hole has become the future, and moving toward it is as inevitable as moving forward in time. The radius of the event horizon, called the Schwarzschild radius, after the German physicist Karl Schwarzschild, who first calculated it in 1916, is proportional to the mass of the black hole. For a black hole with the mass of the sun, the Schwarzschild radius is about 3 kilometers, For a black hole with 10 solar masses, it is about 30 kilometers. Small by cosmic standards. Invisible except by their effects. Stellar mass black holes, those formed by the collapse of massive stars, typically have masses ranging from about 5 to perhaps a few dozen times the mass of the Sun. They are invisible in the traditional sense, emitting no light, but they can be detected by their gravitational effects on nearby objects. When a black hole orbits a companion star in a binary system, it can strip material from its partner, and that material, spiraling inward and heating up as it falls, emits intense X-rays that can be detected by space telescopes. The infalling material forms a swirling disk of superheated gas called an accretion disk, where temperatures can reach millions of degrees. It was through exactly this kind of observation that the first strong black hole candidate, Cygnus X1, was identified in the early 1970s. The X-ray source was found to be orbiting a blue supergiant star, and the mass of the invisible companion was determined to be far too large to be a neutron star. In recent years, gravitational wave astronomy has opened an entirely new window onto black holes. The LIGO and Virgo observatories have detected dozens of merging black hole binaries, pairs of black holes spiraling together and colliding in events that produce ripples in the fabric of spacetime itself. These observations have revealed that stellar mass black holes can be surprisingly massive, with some merging pairs having combined masses of over 100 solar masses. The formation of a black hole marks the most extreme possible end for a star's life. It is a complete gravitational victory, the ultimate triumph of gravity over every other force. And yet, even black holes are not eternal. Stephen Hawking showed in the 1970s that black holes slowly radiate energy through a quantum mechanical process now known as Hawking radiation. Over unimaginably long timescales, a stellar mass black hole would eventually evaporate completely, vanishing in a final burst of particles. But the timescale for this is so long, perhaps 10 to the 67th power years for a solar mass black hole, that for all practical purposes, black holes are among the most enduring objects in the cosmos. They will outlast the stars, outlast the planets, outlast virtually everything else in the universe. And then, in the unthinkably far future, even they will be gone. And so, we come full circle. We have followed the life of a star from its origins in a cold, dark molecular cloud, through the fiery adolescence of the protostellar phase, into the long and stable adulthood of the main sequence, and finally through the dramatic transformations of its old age, whether that means a graceful shedding of outer layers to form a planetary nebula, and a quietly cooling white dwarf, or a cataclysmic supernova that leaves behind a neutron star or a black hole. But the story does not end with the death of any individual star. The material ejected by a dying star, the carbon and oxygen blown off by a red giant, the heavier elements scattered by a supernova, all of it mixes into the interstellar medium, enriching the gas and dust that permeate the galaxy. Over millions of years, this enriched material is gathered up by gravity into new molecular clouds, where the cycle begins again. New protostars form. New main sequence stars ignite. New planetary systems take shape. Each generation of stars produces a slightly higher proportion of heavy elements than the generation before. The very first stars in the universe, formed from the pristine hydrogen and helium left over from the Big Bang, contained no metals at all. Astronomers call these populations 3 stars, and none have been directly observed, although astronomers are searching for them with telescopes like the James Webb Space Telescope. These primordial stars are thought to have been massive, perhaps hundreds of times the mass of the Sun, burning hot and bright and dying quickly, seeding the cosmos with the first heavy elements. The next generation of stars, enriched by the deaths of those first giants, contained small amounts of carbon, oxygen, and other elements. These are the population 2 stars, found today in the oldest parts of our galaxy, in the galactic halo, and in ancient globular clusters, and each successive generation has been richer still in heavy elements, until we arrive at our own sun, a population 1 star, born about 4.5 billion years ago from a molecular cloud that contained enough iron, silicon, carbon, and oxygen to build rocky planets, to build water, to build the complex organic chemistry that eventually gave rise to life. The fraction of heavy elements in a star is called its metallicity, using the astronomers' quirky definition of metals as anything heavier than helium. The Sun's metallicity is about 1.5% by mass, meaning that for every 100 atoms of hydrogen and helium in the Sun, there are about 1.5 atoms of everything else. That might sound trivial, but it made all the difference. Without that fraction of a percent of heavier elements, the molecular cloud that spawned the Sun could not have formed dust grains, could not have cooled efficiently enough to fragment into small clumps, and could not have produced the rocky planets that orbit within the habitable zone. The existence of Earth and of us is a direct consequence of billions of years of stellar nucleosynthesis, billions of years of stars living and dying, and scattering their processed material into the void. We are, in a very real sense, the products of stellar evolution. The calcium in our bones was forged in the core of a massive star that exploded before our solar system even existed. The iron in our blood was produced in the last seconds of a supernova. The oxygen we breathe was synthesized in the triple alpha process, and subsequent helium-burning reactions inside a red giant. The nitrogen in our DNA was a byproduct of the CNO cycle, carried to the surface of an aging star and expelled in its stellar wind. We are not merely observers of the stellar life cycle. We are participants in it. We are made of it, and there is something profoundly humbling about that. We look up at the stars and feel small, insignificant. But in truth, we are not separate from the stars. We are their descendants. We carry their legacy in every atom of our bodies. When we study the stars, we are studying our own origins. When we trace the life cycle of a star, from dust to light to silence, we are tracing the chain of events that led, ultimately, to us. The white dwarfs now cooling in the darkness of space will one day, in the unimaginably distant future, become black dwarfs, cold and invisible, essentially gone from the universe of light and warmth. It will take at least a quadrillion years, a one followed by 15 zeros, for even the oldest white dwarf to cool to the point where it no longer emits detectable radiation. Some physicists have speculated that, on even more extreme timescales, The carbon and oxygen in a black dwarf might undergo a process called pycnonuclear fusion, density-driven nuclear reactions that proceed not from heat, but from the sheer proximity of the nuclei. If this happens, the most massive black dwarfs might, after a period of time so vast it is written with tens of thousands of digits, undergo a final runaway nuclear explosion, a last supernova in a universe that has long since gone dark. It would be the final firework, the ultimate encore, played out to an audience of no one, in a cosmos that has forgotten what light is. The neutron stars will spin down, their pulses fading, their magnetic fields decaying. Over billions of years, even the most energetic pulsars will slow and go silent. The black holes will slowly evaporate through Hawking radiation. And the red dwarfs, the faithful, patient red dwarfs, will burn on for trillions of years, the last flickering candles in a darkening universe. But even the red dwarfs will eventually die. Their hydrogen will run out. They will cool. They will fade. And then, at last, the age of starlight will end. The universe will still exist, filled with dark remnants and cold radiation and the slow ticking of entropy, but the stars will be gone. The universe will enter what physicists Fred Adams and Gregory Laughlin called the degenerate era, an epoch dominated by white dwarfs, brown dwarfs, neutron stars, and black holes, drifting through the expanding darkness, separated by ever-increasing distances as the cosmos continues to expand. It is a melancholy picture, perhaps, but there is also something magnificent about the sheer scope of it. The universe tells its story in chapters so long that the human mind can barely comprehend them. We live in the stelliferous era, the age of stars, and it has lasted barely 13 billion years so far. But it may continue for another 100 trillion years or more before the last star winks out. We are living in the very first moments of a drama that has barely begun. And there is this: every atom that has ever been part of a star will still exist, long after the stars themselves are gone. The carbon, the oxygen, the iron, the gold. They will persist, scattered through the cold and expanding void, carrying within their nuclear structures the record of every fusion reaction, every supernova, every stellar wind that ever blew. The atoms are the memories of the stars, and they will endure. That future is almost incomprehensibly remote. The last red dwarf might not go out for another 100 trillion years. Against that timescale, the current age of the universe, 13.8 billion years, is barely a blip. We are living in the very first moments of cosmic history, the early morning of a day that will last for eons. The stars are young, the universe is young, and there is so much left to happen. But for now, the stars are shining. They are being born in molecular clouds and dying in supernovae. They are fusing hydrogen and building elements and seeding the cosmos with the raw materials for new worlds. The cycle continues, as it has for billions of years, as it will for billions more. In the Orion Nebula, right now, at this very moment, new protostars are collapsing out of the gas, their cores heating, their disks swirling, their jets firing into the void. In the galactic center, massive stars are burning through their hydrogen at a furious rate, destined to explode in a few million years. In the quiet suburbs of the Milky Way, billions of red dwarfs are simmering away, their gentle fusion barely perceptible, their lifespans stretching out ahead of them for trillions of years and scattered throughout the galaxy. The cooling white dwarfs are slowly dimming, their crystalline interiors growing colder year by year, century by century, millennium by millennium. Every phase of this cycle is happening somewhere, right now. Stars are being born, stars in their prime, stars growing old, swelling, shedding their skins, stars dying in silence and in fury. And from those deaths, new stars are rising, built from the enriched debris of their predecessors, carrying forward the accumulated nuclear legacy of 13 billion years of cosmic chemistry, from a cloud of dust to a roaring furnace of fusion. From a furnace to a bloated giant shedding its skin. From a giant to a quiet ember cooling in the dark. And from the dark, eventually, new clouds will form and new stars will rise, and the whole magnificent story will begin again. That is the life cycle of a star. You have been watching the entire history of the universe. If you enjoyed this journey through the life and death of stars, please take a moment to hit the like button and subscribe to the channel. It makes a real difference, and it helps us keep exploring the cosmos together. Leave a comment below and tell us which part of the stellar life cycle fascinates you the most. Is it the fiery violence of a supernova? Can the patient endurance of a red dwarf? The quiet dignity of a white dwarf cooling toward eternity? Or perhaps the strange and beautiful symmetry of the whole cycle, the way the death of one star gives birth to the next? We want to hear from you. Every comment, every like, every subscription helps us bring you more content like this. And it tells us that there are people out there who care about the universe and want to understand it better. If you are still here, still listening, still with us after this long journey through the cosmos, thank you. It means the world to us. And it tells us that the story of the stars is one that still has the power to captivate, to inspire, and to fill us with wonder. Thanks for watching, and we will see you next time.